Okay, so we've established moment of inertia. Just to review, the moment of inertia for point masses, but point mass is going to be the sum of mr squared, and the moment of inertia for solid masses is then the integral of r squared dm. And typically this is going to be given to you. So here's a table that lists the moments of inertia about certain axes of rotation. There are two derivations that you need to know. One is this one, a cylindrical rod, and then the other one is going to be this sphere. A shell. So I'll go through this one later on, and then this one I think I'm going to leave for Mr. Winter to go through in class. But what we're going to talk about right now is called the parallel axis theorem. And the parallel axis theorem is pretty useful because what it does is it relates the moment of inertia through the center of mass to any other axes which is parallel to it. So while the cylinder gives me the moment of inertia through the center, like this one gives me it through the center, if I were to shift this and I knew that the moment of the axis of rotation was shifted over by a certain little r, then I could calculate the moment of inertia about that point. And I could do it anywhere. I just need to know where are you shifting it to, as long as it's parallel to the axis of rotation through the center of mass. And so the theorem says that the moment of inertia through a parallel axis is equal to the moment of inertia through the center of mass plus the mass times the distance it's been shifted squared. So let me label this stuff. So this is the amount about a parallel axis. And then this is the moment of inertia about the center of mass axis. And the d is the shift, how far it's been shifted. So pretty simple. If we know the inertia through an axis through the center of mass. Gosh, that's a mouthful to say. Okay, so how do we use this? It's relatively easy. So we either know the moment of inertia somewhere, and then we want to find the one at the center of mass, or we know the center of mass. So what I want to do as an example is to show you. We'll do this one. So what we're going to do is we're going to use the parallel axis theorem to go from this one over to this one. So a solid rod about the middle is 1/12, and when it's been shifted to the end, it would get 1/3. So let's go through. We're going to use the parallel axis theorem to do that. So I'm going to sketch it out real quick. Okay, so I have our situation drawn out. So we're given this one. This is a cylindrical rod, a thin rod, axis of rotation through the center of mass, and the equation for it is given by 1/12 mass times the length squared, solid mass. And it's uniform mass. That's important whenever we do this. So we can only deal with uniform mass. And what we want to do is we want to shift the axis over to the end and determine the equation for the moment of inertia. And so we would use the parallel axis theorem in this case. So the parallel is going to be the moment of inertia about the center of mass, this thing, 1/12 ml squared plus the total mass times the distance of the shift. And so be careful with this. So what we've done is we've actually just shifted at this distance, which is 1/2 of the length. So it'd be 1/2 of the length squared. And so now we can simplify. We get 1/12 ml squared plus 1/2 squared is 1/4 ml squared getting common denominators, that would be 12, so 3. So we end up with 4/12 ml squared, which simplifies to 1/3 ml squared. And then we can verify that. We can go up to our table and see that, yes, it is 1/3 ml squared. So this works for anything. So like this plate, if I wanted to know, here we are this is through the center of mass. If we shift this axis, say, I don't know, let's go over here. So we're going to go through the edge. I'll do another one just to see. So we're going to go through the edge. Then my moment of inertia, I don't have room. Hold on a sec, let me erase this over here. All right, so my moment of inertia of the parallel is going to be this thing, 1/12 m times a squared plus b squared plus m times the distance I moved it. So I moved it 1/2 of b squared. And then we would go through our simplification if we could. I don't know, let's just do it. So 1/12 m a squared plus 1/12 m b squared plus, that's 1/2 squared is 1/4 m b squared. So we can put those two together. So we're going to get 1/2 m a squared plus, that's going to simplify to the same, 1/3 m b squared. And well, we can leave it there. So anyway, that's how the parallel axis theorem works. It always has to be, just remember, it has to be parallel to your original axis, and it's the one through center of mass. If you're going the other way, if you know the equation at the end, like 1/3, then that would just be over on this side. So you would subtract md squared. So that's the parallel axis theorem. Okay, now I want to walk you through a derivation for this moment of inertia. So let me clear this. And you do have to know this derivation, so you need to practice this thing. Okay, so we're going to have a rod rotating about its end. So it's of length L. And the axis of rotation, again, is at the end. It's the easiest place to do it. Okay. So what we want to do is the moment of inertia is going to be the integral of r squared dm. That's given. That's the definition. So for this one, what we're going to do is you integrate, the integral moves away from the axis of rotation. So my integration needs to move in this direction. So we're going to integrate from 0 to L. Now the thing is that this dm is not in terms of L. That's not in terms of length. So we need to do some stuff with this dm. So let's slice it up. And so if we take a little piece of this thing and call it dm, so it's a little sliver of the mass. So that's dm. It's just a little piece of it. And then because this thing is uniform density, we can go through density. So density rho is your mass over your volume. Now the density is the same, so it doesn't matter how much mass and volume I have. The ratio is always the density. So if I have a little bit of mass and a little bit of volume, then the density is the same. And so I can rearrange this and I'll get that the little bit of mass is equal to rho little bit of volume. So now I can change this to volume. So we can do, the inertia is going to be from 0 to L of r squared rho dv. All right, so v is still not L. So now we need to change it so that we can get it in terms of L. So thinking about that, what we have, we can look at the volume of this little thing, or actually of the rod. So the volume of the rod is going to be the area, and we're talking about this area right here, times the length. But what we're going to do is we're just talking about this little piece. So it's the area here times some little dl. So the volume is going to be the area times dl. And now we can substitute that in here. So the moment of inertia is going to be from 0 to L of r squared rho, and I'm sorry, this is a little piece of the volume, area times dl. We can pull out some constants before we integrate, because density is a constant. The area is the area over here, that's constant. So we get rho a integrated from 0 to L of r squared dl. Okay, so now we can integrate. So rho a, that's going to be 1/3 r cubed integrated from 0 to L, which is 1/3 L cubed. Now the thing is, all of our moments of inertia, if you notice, they're all some number, mr squared. So we need to change some stuff here. The r here in this case is L, but you get the idea. It needs to look like this. So we want to redefine stuff in terms of mass. So we can go back to our density. So density times volume is equal to mass, and volume is area times length, and that's going to be mass. So what I want to do is I want to break off one of these L's and put it over here. So we get density times area times L is 1/3 L squared. So this part right there is mass, that's what we just said. So we get 1/3 mL squared. And that's our moment of inertia. So the tricks, if you will, are right here. So this one we used to substitute here. And then this one gave me dV in terms of dl. So we were able to switch it to dl. So that one was where? Here. And then finally we put this one here. So that's our derivation for a uniform rod. Now to get it to the center of mass, if I wanted to do that, I could use the parallel axis theorem. So a good free response might be to, given this information, derive this and then show that the through the center of mass is equal to this. But whatever, there's your derivation.